Okay. So indeed, I will talk to you about how to consider carbonate burial in blue carbon budgets in seagrass meadows. And this is a collection of recent work we are doing with all these co-authors, including Paul and Ariane and Michael over there, and I think it's all. And so here it is. So you all know what is blue carbon, I guess, by now. So accretion of particles from outside, from inside. Accretion rates for the last 100 years measured with lead-210, about 0.3. For the last centuries to millennia, about 0.1. Long-term sequestration of organic carbon in sediment that leads to a net uptake of CO2 from the atmosphere. Okay, the thing is, organic carbon in sediment, it's only 2 to 3% of the dry weight. And that means that all the rest is mineral. It's either silicate or carbonate. So carbonate, it's calcium carbonate, and inorganic carbon in this is 12% of the mass. So most of carbonates on Earth come from biogenic calcification in the sea. And the thing is, and it's quite counterintuitive at first, is that calcification process emits 0.6 mole of CO2 to the atmosphere per mole of calcium carbonate precipitated under nowadays atmosphere. And this is due to the fact that there is more consumption of alkalinity than of DIC after reequilibration with a 400 microatmosphere PCO2 atmosphere. So the thing is, all this calcium carbonate and inorganic carbon we find in seagrass sediment, is that a CO2 source, and how can we take it into account? So what we did is a meta-analysis of the burial rates of calcium carbonate or inorganic carbon in seagrass meadows. So this is a subset for those who have seen the presentation of Ariane yesterday. We are still recycling the same value in all meta-analysis. So this is actually a subset of Ariane's value because everybody measures organic carbon, but not everybody measures inorganic carbon. So we obtained 71 cores dated with carbon-14 in 16 world locations, and 51 core dated with lead-210 in 17 world locations. Plus, we have 32 locations where we have cores with only the calcium carbonate content, no geochronologies. Okay, so this is the frequency, the histogram of distribution of frequencies. So what we see on that at first is that it's not a normal distribution at all, and that in about 40% of the world locations we have between 0 and 10% of calcium carbonate in the sediment. Now, in 30% of the world location, we have between 80 and 100%. So as a metric of the central tendency, we use the median because it's not normal. So if we pull all that together, the CaCO3 content in world seagrass sediment is about 60% dry weight, what is a lot. This is all the locations with the burial rate for lead-210 and carbon-14 ranked by latitude from low to high. So I will come back to it, so I'm just passing by on that very fast. For the moment, I will just pull everything together and get a world value. So when we do that, we get a carbon-14 value of 30 grams per square meter and per year, and a modern lead-210 of about 90 grams per square meter and per year. And this difference is due to the fact that the modern sediment accretion rate is about 3 times higher in our data set than the long-term one. And this is quite normal. Again, we are always recycling the same data, so it makes sense that it's like published data. You all know these estimates of global seagrass coverage, and you all know what it's worth. If we multiply the burial rates by this coverage, at the end, we get about 13 to 50 teragram of carbon per year as a burial rate over the first meter. If we compare with already published estimates of burial rates of organic carbon, that is 48 to 112, and we apply the rules of the 0.6 CO2 emission. If we consider that all this carbonate comes from the seagrass meadows, nothing comes from somewhere else, then we have a reduction of 17 to 33% of the CO2 uptake by seagrass ecosystems. Now, if we use the estimates of Aryan that Aryan shown yesterday, then you can forget about blue carbon, it doesn't exist. Okay, that's not the end of the story. Let's go back to these histograms. So there is a large geographical disparity, as you can see. There is a lot in the low latitudes and far less in high latitudes. Actually, in tropical and arid climate locations, it's 90% of the global burial. In higher latitude, it's only 10%. So I'll take an example of what we did in the Red Sea and the Arabian Gulf. Very quick. Over there, about 60% of the sediment is calcium carbonate. In the Gulf, so only in the Gulf, we have about 130 grams per square meter and per year of burial of inorganic carbon, about only 9 grams per square meter per year of organic carbon. So if we apply the 0.6 rule, then it's a net emitter of 70 grams per square meter and per year. The problem is when you own the field, it's very obvious that this sediment doesn't come from the seagrass, it comes from the coral reef just beside. And it's obvious because you go in the mangrove, it's the same, and you go in this dry salt marsh, still the same. You find the same content of calcium carbonate. This comes from you find blocks of reef, actually. So where does the carbonate come from? This is the real question. So what we did, is very simply, we looked at the influence of the presence or absence of very easily identifiable source of carbonate around the coring location we have, and we compare it with the percentage of calcium carbonate in the sediment. So we used maps that exist that you can consult yourself. It's the map of the FAO for soils that is very detailed, the map of the coral reef in the world, and the geological maps of the USGC. And when we do this, what we see is in area when there is no obvious sources of carbonate around the coring location, we end up with only 4% of calcium carbonate in the cores. In any other cases, we are around 50 and 80%. So if we look at this repartition, this is actually correspond to generally high latitude without calcareous bedrock around. And I took as an example Hokkaido in Japan. All the rest, it's either high latitude with calcareous bedrock, like the Balearic Islands, for example, or intertropical with a coral reef and or a bedrock around. And I took Ishigaki in Okinawa. So the presence of external sources seems to explain very well the calcium content in seagrass sediment. So that means the calcium carbonate is imported. Now I know there is calcification in seagrass meadows. I'm not saying the opposite. There is. The question is, what is the amount of it? And the problem is, it's difficult to say because there are not a lot of studies about that. And I will take two examples. So, two locations, the Balearic Islands and Shark Bay in Australia. So, why these? It's because I have net production of calcium carbonate in the meadow, gross, meaning after balance with dissolution, and the sediment accretion rates from the data I have. They are both genus Posidonia that are known to have very high epiphytic loads and a very strong calcifying community associated. And one is temperate, the other one is arid. If we make the comparison, the calcification rate explains about 3% of the burial in the Balears and 20 to 30% in Shark Bay. So, as conclusion for the moment, well, what we can see first is that calcium carbonate is an important contributor to seabed elevation with 60% dry weight globally. And it's especially true in a region like the Arabian Peninsula where it rains like 3-4 times a year where I am. So there is no surface runoff and all the sediments come from weathering of the coral reef. Except for aeolian influence, I mean, it exists. Burial rates of inorganic carbon cannot be translated into CO2 emissions. I think this is the most important. I mean, don't calculate the accretion rates multiplied by the carbonate content and say 0.6 and then get a CO2 emission out of that. This doesn't work. What we need is studies on net calcification rates, and we need to be tracking the fluxes of calcium, actually. And to finish, there is actually a good news about it, is that since it seems that there is a lot of imported calcium carbonate, and that seagrass meadows are places of very high diurnal variations of the CO2 systems, what can happen is actually this imported carbonate may dissolve in the seagrass meadows. That's even more true for the mangrove. And this might be actually a hidden sink of CO2. This is an example of my past work in the Baltic. This is 2 months of omega aragonite and calcite variations. And what you can see is that part of the day we are below 1. So the sediment can dissolve. So that's it for the moment. Thank you.
Thank you, Vincent. We have time for some questions. Barry and then Anitra. Oh, Anitra, off you go first.
In areas where there are not lots of coral reef intrusion in the Gulf of Mexico, which would be in the Texas coast, there are enormous amounts of micro shelled animals, foraminifera and other protists that live on and around the seagrass, and when you pick up the quartz sand that they're buried in, you see enormous amount of shells and broken shells and so forth. So there is some kind of diagenetic source happening right there besides the thalassia, which is not reported.
I'm not saying the opposite. That's also one of the problems. A lot of people, what they do is they look at the epibionts and calculate from the turnover rate of the leaf or whatever. And what you're telling me is that we need to take into account the whole community, including the benthic foraminiferas in the sediment. Yes, absolutely. I mean, there is calcification in the seagrass meadow. I'm not saying the opposite. I'm just saying that you don't explain 60% of the world with that. That's it. I mean, after we can discuss of special cases. I haven't been in most of location I'm showing, of course. I mean, I'm just referring to maps, and in the other end, it's a method, you know, like.
Saying when you take an example, if you're worried about the coral reef, then you shouldn't take it from the areas with coral reef. You should take it from the areas without coral reef and see what's happening there in Texas would be the part.
Yeah, but the problem is I don't have that many coring location either. I mean, it's limited. But what I can tell you is that from a global point of view, it works extremely well. I mean, we have 4% versus 50 to 80%. So but yeah, I mean, this is it's always we had a very long debate with one of the co-author about Florida Bay, for example. Because Florida Bay is very interesting. There is a lot of calcification happening there, and the budget is extremely difficult to equilibrate. And actually, it doesn't at all. When you compare the burial to the production, we have a 90% of difference. So we don't know. So, but I guess, yeah.
Well, I guess you've heard more or less the evidence of that also carbonate formation in the
Yes.
surface reduction to also take into account.
Okay.
But the other thing I should consider that this general concept of when carbonate forms is CO2 released and it's a net source and so forth, what hasn't been really considered or talked too much is that certain plants, not seagrass as well as things like alameda, which may can produce a lot of carbonate in seagrass beds, you get a lot of recycling based on the lacunae of the leaf. So even though it's carbonate we measure, it's turning into organic matter.
I don't know if I understand well, but the thing is, we shouldn't think in terms of CO2, we have to think in terms of DIC, because it's the same. This CO2 emission is not really a CO2 emission. I mean, you have to consider DIC and the speciation of DIC. Like, it doesn't matter whether it is really CO2. I mean, the seagrass, they uptake bicarbonate, for example, because it's not interesting to feed out of CO2. It's not even 1% of the DIC. So the thing is, you have to think in terms of DIC. It doesn't matter whether the organism reuse its respiratory CO2 to do calcification, whatever, through carbonic anhydrase. At the end, it's DIC. And this is all that matters. The balance between DIC and TA and the fact that we are in 400 microatmosphere PCO2. And when you do the calculation, it's easy to do. You'll see it works. The 0.6, I didn't know about it. I started to do a calculation. I found it. And then I said, oh, yeah, indeed, that works. You can try it. It's very easy to find this 0.6.
Well, you've sorry, but you've convinced me, Vincent, and maybe you can convince Barry over a cup of coffee later on. Great. Could you join me in thanking Vincent?